module, you will learn about sequences and series. Take a look at the collection of numbers shown on the screen. Can you make out the order or the rule in which the numbers are listed in each collection? In the first collection, all the natural numbers are listed in ascending order. In the second collection, all the multiples of 5 are listed in ascending order. The third is a collection of the first 5 even numbers. And in the last one, the collection of squares of first 5 natural numbers has been listed. In each collection, there is a specific rule or order in which the numbers are listed. When a collection of objects is listed in a sequential manner or a definite order such that every member has a definite position, that is, it comes either before or after every other member, it is called a sequence. A sequence can also be defined as a collection of numbers arranged in a definite order according to some definite rule. The members or numbers that are listed in the sequence are called its terms. The terms of a sequence are denoted by A1, A2, A3 and so on up to AN, where A1 denotes the first term, A2 the second term, A3 the third term, and AN denotes the nth term of the sequence. For this sequence, 5 is the first term, 10 is the second term, 15 is the third term, and 35 is the seventh term. Observe that the subscripts denote the position of the terms in a sequence. If we say the nth term of a sequence, it means that the term is at the nth position in the sequence. The nth term is denoted by A, with subscript n. An is also known as the general term of the sequence. A sequence is finite or infinite, depending upon the number of terms in it. If the number of terms in a sequence is finite or countable, then it is called a finite sequence. And if the sequence goes on forever or has an uncountable number of terms, then it is called an infinite sequence. For example, the sequence of natural numbers and the sequence of all the multiples of 5 is an infinite sequence. However, the sequence of the first 5 even numbers and the squares of the first 5 natural numbers is a finite sequence. The terms of a sequence can be expressed by an algebraic formula. For example, consider the sequence 1 by 2, 1 by 4, 1 by 8, 1 by 16, and so on. The first term of this sequence, 1 by 2, can be written as 1 by 2 raised to the power of 1. The second term, 1 by 4, can be written as 1 by 2 raised to the power of 2. The third term, 1 by 8, can be written as 1 by 2 raised to the power of 3. The fourth term, 1 by 16, can be written as 1 by 2 raised to the power of 4. Similarly, we can write the succeeding terms. In this way, we can say that the nth term of this sequence can be expressed as 1 by 2 raised to the power of n, where n is a natural number. Using this nth term of the sequence, we will be able to find any term in it by substituting the term value in place of n. Thus, the 8th term of this sequence is given by 1 by 2 raised to the power of 8, which is equal to 1 by 256. In some cases, an arrangement of numbers in a sequence like 1, 1, 3, 7, 17, 41, and so on has no apparently visible pattern. But the terms of this sequence are generated by the relation given by A1 is equal to A2 is equal to 1. The third term can be obtained by adding the first term and 2 times the second term. The fourth term can be obtained by adding the second term and 2 times the third term. In this way, we can obtain the nth term of this sequence by adding the n-2th term and 2 times the n-1th term for n greater than 2. Likewise, we can describe the sequence 1, 1, 2, 3, 5, 8, and so on as shown. This sequence is known as the Fibonacci sequence. Sometimes, it is practically impossible to express the terms of a sequence by means of a particular algebraic formula. Such sequences can only be described verbally, like the sequence of prime numbers 2, 3, 5, 7, and so on. A sequence is a collection of all images of a function x from n or any subset of n to x, where n is the set of all natural numbers and x is any set, maybe of objects, events or numbers. It implies that the domain of the function is the set of natural numbers. Hence, a sequence can be defined as a collection of all images of set n under x. The notational representation of 1 under x is denoted by x with subscript 1. Similarly, the image of 2 under x in notational form is written as x with subscript 2. And likewise, we denote the sequence as shown, where the subscripts denote the position of the terms in a sequence. Sequences are also called progressions because the terms in a sequence progress in a definite manner, obeying some specific algebraic rule. Let us now learn about series. Consider a sequence with the terms A1, A2, A3, A4, and so on. Then, the expression A1 plus A2 plus A3 plus A4 and so on up to AN is called the series corresponding to the given sequence. Mathematically, the expression obtained on adding the terms of a sequence is called a series. Here, A1 is called the first term, A2 the second term, and AN is called the nth term of the series. A series is finite if the given sequence is finite, and infinite if the given sequence is infinite. In summation notation, the infinite series A1 plus A2 plus A3 plus A4 and so on up to infinity can be abbreviated as sigma AN, where n is from 1 to infinity. Similarly, in summation notation, the finite series as A1 plus A2 plus A3 plus A4 and so on up to AN can be written as sigma AK, where k is from 1 to n. The summation representation of a series is also known as the compact form of the series.